Okay, this is day 3 notes and it covers Gay-Lussac's and the combined gas law. The goals for this section is that you can explain the gas properties as they relate to the Gay-Lussac's and combined gas law, and also be able to calculate some of these variables by solving algebraically with some given equations. So first, to start out, Gay-Lussac's law deals with pressure and temperature and the relationship between the two. So the law that describes the relationship between temperature and pressure is named after him because that's the work that he did. He said for a given volume of gas, as the temperature of a gas increases, the pressure of the gas will also increase. He used the terms directly proportional, which is probably a little bit more specific. So as temperature increases, the pressure will also increase. We can simplify the relationship by looking at it like this, where P1 and P2 are the pressure. Those can be in any units, but they have to be in the same unit. T1 and T2 are the temperature, and that's always going to be in Kelvin. And like you saw before, you just add 273 to any temperature in Celsius to get that temperature into Kelvin. So looking at an example, a gas has a pressure of 103 kilopascals at 25 degrees Celsius. What will be the pressure when the temperature reaches 928 Celsius? So we can identify the variables. We're working with pressure and temperature here. The initial pressure is 103 kilopascals. The initial temperature is going to be 25 degrees Celsius plus 273 in order to convert it to kelvins. That makes it 298 Kelvin. We don't know the new pressure, but we do know that the new temperature is going to be 928 degrees Celsius plus 273, so 1201 Kelvin. The equation looks like this, and now it's just a matter of plugging in the variables. We have 103 kilopascals over 298 Kelvin, and that's going to equal that pressure, which we can make X over 1201 Kelvin. You can cross multiply and solve for that second pressure, and you'll get 420 kilopascals. So as you can see, as temperature increases, pressure is also increasing. The next gas law that we're going to talk about is called the combined gas law. And the combined gas law takes all 3 of the laws that we've looked at so far and puts them all together. So it describes the relationship between the 3 variables of pressure, temperature, and volume. And what's nice about this is it allows you to do any type of calculations where the amount of gas, so that's the moles of gas, is constant. The combined gas law, oh gosh, it's hard to see. It looks like this. So it's P1 V1 over T1 is going to equal P2 V2 over T2. So P1 V1 over T1 equals P2 V2 over T2. What's nice about this is that you don't need to memorize each of the individual laws. You can just cover up whatever variable you're not using, and that will leave you with the rest of the variables. So all you really need to know is the combined gas law, and from that you can get the others. And there it is again. So for example, if you have a problem where there's no there's no mention of temperature, then you can just cover up the T and you're just left with the relationship between pressure and volume, which is Boyle's law. So P1 V1 equals P2 V2. If there's no mention of pressure, then you cover up the P and now you're left with the relationship between temperature and volume, or Charles' law. So again, we can cover up the pressure. Now we have V1 over T1 equals V2 over T2. Finally, if there's no mention of volume, same thing, we can cover up those, and now we have P1 over T1 equals P2 over V2. And again, that's called the combined gas law. Let's look at an example problem. A gas occupies 3.78 liters at 529 millimeters of mercury and 17.2 degrees Celsius. At what pressure would the volume be of the gas be if 4.54 liters of the temperature is increased to 34.8 degrees Celsius? So there's a lot going on with that problem. The first step is to just write down all of the potential variables that you have and identify them. So initially we have 529 millimeters of mercury as the pressure. The volume is that 3.78 liters. The temperature has to be in Kelvin, so we take the 17.2 and add 273. So you get 290.2. We don't know the new pressure, but we do know the new volume, 4.54 liters, and we can calculate the new temperature, 34.8 plus 273, so we have 307.8 Kelvin. there's the equation, and it's just a matter of plugging in all the variables where they go. And then we have to solve for that P2. We solve that algebraically, and you'll get 467 millimeters of mercury. If there's any questions, please don't hesitate to send them my way. Otherwise, this corresponds to worksheet number 3.